Sir, as a customary, I need to introduce a man who needs no introduction. Uh, Participants, we are fortunate today to have Professor Dilip Kumar Pratihar as the expert speaker for this particular session. At the outset, on behalf of our Department of Production Engineering, BSCUT, and the team of this Atal FDP, alongside the participants, I would like to congratulate Sir for being awarded the INSA Teachers Award 2020. Congratulations, sir.
Okay,
The
thank
award
you.
really
Thank you very much.
deserves you. As a customary, let me read out this thing that sir has already, he has completed his PhD from IIT Kanpur in 2000. And now the people like in my generation, whenever we think of this soft computing, only one name comes to our mind, that is Professor D.K. Pratiyar, because we all follow your books, sir. Uh,
Thank you.
Sir is working now as a senior professor of IIT Kharagpur. His research areas include robotics, soft computing, manufacturing science, and others. He has made significant contributions in the field of computational intelligence. He has published 160 research papers in peer-reviewed international journals and more than 100 papers in conferences and national journals. He has contributed 18 chapters in edited international book. A few of his fundamental contributions published in IEEE, ASME, Elsevier, Springer Journal are being highly cited, not to mention. His H-index value are found to be 36 in Google Scholar and 26 in Scopus. He has written the textbook on soft computing that we all follow, Fundamentals to Robotics, authored textbooks on analytical engineering mechanics, edited a book on intelligent autonomous system, co-authored 4 reference books on modeling and analysis of six-legged robots, modeling and simulation of robotic systems using soft computing, modeling and analysis of laser material forming process by finite element and soft computing methods, and multi-body dynamic modeling of multi-legged robots. His textbook of soft computing has been translated into Chinese language also. He has developed 3 online NPTEL courses such as traditional and non-traditional automation tools, robotics and fuzzy logic, and neural networks. He has guided 22 PhDs. He has completed a number of sponsored projects funded by DST, DAE, DBT, MHRD of Government of India, and 2 consultancy projects of industries. He has filed 2 patents. Uh, he is in board editorial board and has been appointed as associate editor of few international journals. So, without wasting much time, let me welcome Sir to this particular session. So, thank you for accepting our invitation and agreeing to take a session in this FDP program. I welcome you, sir, and request you to start the session. Please, sir.
Okay. Thank you, Professor Mahapatra, for introducing me. And I'm grateful to the organizing committee for giving me this opportunity to share my ideas. And these ideas in India, we started in the year 2000. Might be we were the first person to think on input-output modeling of any engineering process. I remember we started in 2000. Okay. Now, before I proceed further, let me tell you a few things. As I'm unable to use the board, I'll request you one thing. All of you, all the participants, please maintain one notebook side by you and along with a pen. So use one notebook and a pen. Okay, whenever I'm just going to deliver this lecture, I'm just going to give you a few instructions which you'll have to write on the notebook, and you'll have to draw a few things also. Okay, because I'm not getting the opportunity to use my board here. Okay, so please maintain one notebook and a pen side by side. You keep it. Okay. Now, another thing I should tell that let me talk for the first 1 hour, 40 minutes or 45 minutes. Okay. And if you have any doubt, please note it down on your notebook. Okay. And then at the end, might be the last 15 minutes or 20 minutes, I'll level best to clear your doubts. Okay, so please follow this. That will help me because this topic is very wide. Okay, in fact, to teach this particular topic, I need, in fact, a minimum of 20 hours lecture. Okay, and that I'm going to cover might be less than 4 hours or 4 hours. Okay, so listen to me, and I'll try my level best to give you the maximum within this particular the minimum time. Okay, so today I'm just going to talk on input-output modeling of manufacturing processes. Am I audible to all of you? All of you can follow me? Can you follow me? Okay,
Yes, sir.
fine.
You're audible.
So I'll be talking on input-output modeling of manufacturing processes. Now the methods which I'm going to discuss is not only applicable to manufacturing process, but it is applicable to any engineering system or any engineering process. Now this is the structure of my talk. First, I'll give a brief introduction to the problem of input-output modeling. Then I'll concentrate on the conventional regression analysis, how to establish the input-output relationship using some conventional statistical method. And I'll try to find out its advantage and disadvantage. Then I'll switch over to unconventional or non-conventional regression analysis using the concept of fuzzy logic and neural networks. And some case studies will be discussed. Now to start with, let me tell you, why do you need this input-output modeling in the forward direction as well as in the backward direction? Now to start with, let me take a very practical example. I think all of you might have seen, or might be all of you have done little bit that particular work. Okay. Now, supposing that we want to do some sort of machining, okay, on some cylindrical job, and I'm just going to use a lathe, and I'm just going to do the simplest of all machining operation, that is the straight turning on a lathe. And what is the purpose of straight turning? The purpose of straight turning is to reduce the diameter of that particular shaft, and at the same time, the surface finish should be very good. That means the surface roughness should be as minimum as possible. Now, how to do that? If you just rely on one experienced operator, how does he do? So the way he does, on the lathe, he will be selecting a few parameters. What are the parameters? The parameters are nothing but the cutting speed, feed, and depth of cut. Okay. So depending on the requirement, the operator is going to select cutting speed, feed, and depth of cut. Okay. And he will be doing the turning on the lathe, and he will be getting a particular very good turn surface. Okay. A turn surface with very good finish or the minimum surface roughness. Okay. Now, how does he select that? How does an experienced operator can select that if this is the requirement of the quality of the turn surface, how can he select that particular input parameters, that is cutting speed, feed, and depth of cut? So I hope you have understood the physical significance of this particular, the input-output modeling. Now, what do you do in input-output modeling, and why do you need? Now, remember one thing, we human beings, we have a natural quest or a thirst to know input-output relationship of any engineering system or any process. Okay. Now, what does it mean? It means that if I know the set of inputs, how can I predict the set of outputs? And knowing the inputs and finding out the outputs is nothing but the forward modeling or the forward mapping. So this input-output modeling could be either in forward direction or in the backward direction. Now, knowing the from input to output, if I just move, that means if I just do the mapping from the inputs to the outputs, that is nothing but the forward mapping, and it's reverse. That if I want to reach a set of output, how to select the set of input? That is what we mean by that reverse mapping or the reverse modeling. Now remember, that particular experienced operator working on the lab, he is conversant with this input output relationship, okay, in both the directions. So he is having some knowledge base, and he is having some expert system in his mind, in his brain, that if this is the set of input, what could be the output? And if I want to reach or obtain this set of output, how to select this particular the input? And that is why he is an experienced operator, and we are dependent on the experienced operator. Okay, are you getting my point? So if you want to automate a process, like for example, say the state turning process, if you want to automate, that means there is an automatic way of selecting the input parameter to reach a set of output. So this input output relationship are to be known in both the direction. So input output modeling is required for a manufacturing system or any engineering system if you want to automate that particular system or a process. Okay. Now, let me take a very simple example. One optimal decision of that particular the experienced operator working on the lathe or state turning. Okay. Now, supposing that my requirement is such that I want a very good surface finish on the turn surface. That means your surface roughness has to be as minimum as possible. Now, if you give the task to this particular operator, he will be selecting cutting speed, feed, and depth of cut in such a way so that that you get that desired surface finish on the turn surface. Okay. Now, what could be the optimal the decision or the optimal rule which he is going to follow? If you want to get a very good surface finish, okay, with minimum surface roughness, might be the cutting speed has to be very high, the feed has to be low, and the depth of cut has to be low. So if he wants to get a very good surface finish, might be he is going to select the cutting speed on the lathe to a very high value, the feed rate to a low value, and the depth of cut to a low value. How can he decide that type of rule? He can decide because he is having that particular experience or expertise based on this particular input-output modeling. So I hope I am able to give you some introduction to this particular problem and why do you need this input-output modeling both in the forward direction as well as in the backward direction. And let me repeat, it is required just to automate that particular engineering system or the process or that particular manufacturing process. Now, if you see the literature, a huge literature is available, like how to express the input-output relationship using the conventional or traditional regression analysis. And this is also known as the conventional or the traditional statistical regression analysis. So I'll be discussing little bit in more details in the next slide might be. But before that, let me tell you, this particular conventional or traditional regression analysis has got a few advantages, at the same time a few disadvantages. And that is why like we just switch over to the unconventional or non-traditional regression analysis using the concept of fuzzy logic and neural networks. Okay, so I'll be discussing in details how to carry out like both the forward mapping as well as the reverse mapping using the principle of fuzzy logic and neural network. But before that, let me tell you that forward mapping could be very easy using the conventional or the traditional regression analysis, but it may not be always possible to carry out the reverse mapping based on the equation obtained through the statistical or the conventional or traditional regression analysis. That is why we'll have to depend on unconventional or non-traditional regression analysis. Now, these are also statistical analysis, but these are called unconventional or non-conventional regression analysis using fuzzy logic and neural network. And you'll be astonished to know both the forward mapping as well as the reverse mapping can be carried out very efficiently using the principle of fuzzy logic and neural networks. So I'll be gradually coming to that. But before that, let me tell you, in short, the method which we follow to carry out the conventional regression analysis. Okay. Now, how to carry out this conventional or the traditional or the statistical regression analysis? Let me try to take a very simple example, very practical example. Okay. Now, remember, in this course, where I'll be getting the opportunity to interact with you only for 4 hours. So I have decided to take many practical examples so that you can visualize that particular problem instead of going for the mathematical treatment. Okay, mathematical treatment I've already kept in my textbook on soft computing, and I've already kept in my NPTEL lectures. So I'll be coming to that after some time. But I'll be mostly taking the practical example so that things become very easy for you to understand and visualize. Okay. Now, to start with, let me tell you, let me take another very practical example. I think all of you might have seen during in front of any such puja pandals or festival pandals or any other pandals, you might have seen that we take the help of a few pillars. Okay. So we simply put a few pillars, and at the top of the pillars, we put some sort of polythene sort of thing or some curtain sort of thing, just to find out a temporary roof for the visitors or the persons who are attending that particular meeting. Okay. Now, how to select the number of pillars and why do you select that particular pillars? We select the number of pillars for the tent, okay, or we select a few pillars for the tent so that we can put that particular tent as nicely as possible, as tightly as possible. Okay, are you getting my point? Now, how to select the number of pillars and why do you need that number of pillars? Purpose is very simple, so that I can put that particular tent in a very nice way, in a very smooth way. It can cover the maximum area. Okay, are you getting my point? Same is true here. To carry out the conventional regression analysis, we try to select a few pillars so that at the top of the pillars, we can put a tent as nicely as possible. That particular tent is nothing but the surface of the regression equation. Are you getting my point? So we want to put a few pillars, and at the top of the pillars, we put the tent. That means we want to select a few primary experiments designed in a statistical way. How to design? I'm coming to that. Okay, so that I can put one regression surface as accurately as possible. Are you getting my point? Now, those pillars are selected in conventional or statistical regression analysis following some method. Those are known as full factorial method, half factorial method, central composite method, and so on. There are many other methods. Okay, let me take another very practical example. Okay, so I'm going to take a number of practical examples so that things become very easy for you. Now, you are attending this lecture sitting in a particular room. Okay, please look into any of the corner of the room where you are sitting. Please look at any of the corners. What can you see at the corners? You can see that corner is nothing but a junction of three axes. We have got x-axis, y-axis and z-axis. I think all of you are able to see. Okay. Now, if you can see x-axis, y-axis and z-axis, supposing that along x, I have got one variable x1. Along y, I have got another variable x2. Along z, I have got another variable x3. Okay. So, there are three variables. Okay. Now, for each variable, you consider a particular range. So, the range will be different for different variables, x1, x2 and x3. Now, in the range, we have got the minimum value and the maximum value. That means for x1, there is x1 minimum, x1 maximum. For x2, I have got x1 minimum, x2 minimum, x2 maximum. For x3, we have got x3 minimum and x3 maximum. Okay, I think I am clear to all of you. Okay, now if you see the space, the design space, that is nothing but the volume of that particular room. Okay, so with the help of these x1, x2 and x3, I am going to cover a volume that is nothing but the volume of this particular the room. I think I am clear to all of you. Okay. Now inside the room in which you are sitting now, you look into all the corners, like the floor corners, okay, and the roof corners. How many floor corners are there? If it is of rectangular shape or the square shape, there are 4 floor corners. Am I correct? And at the top, on the roof side, if you can see, there are 4 more corners. So 4 plus 4, there are 8 corners. Are you getting my point? Now those 8 corners, if I concentrate on, that is nothing but is your full factorial design. Are you getting my point? So full factorial design is nothing but these 8 corners. Okay. Now half factorial or fractional factorial. Now physically what? This is the half of the total. If full factorial is 8 combination of the input parameters. Are you getting my point? So half factorial is nothing but half of that. That means the 4 combination of input parameters. Okay. What is central composite design? Very simple. Okay. So what we do is, except this, besides these 8 corners, how many faces we have? I have got one is at the top, that is the roof. Another is on the floor. Second one. Third is on my left side, there is a wall. Right side, there is another wall. My front side, there is one wall. Back side, there is another wall. There are 6 such walls, or there are 6 such faces or surfaces. Okay. You try to find out the center of each of these surfaces or each of these faces. So how many centers will be getting? There are 6 faces, 6 surfaces, so there will be 6 centers. So 8 plus 6 is how much? 14. Okay. And at the middle, okay, now x1, x2, x3 has got minimum and maximum. So definitely there is the mid value. Okay. So at the center, you consider the minimum of 3. Why 3? Because I have got 3 variables. Okay. Now what is the total number? 8 plus 6, 14 plus 3, 17. That is nothing but is your central composite design. I think I am clear to all of you. Okay. Now what I do is, whether you are following the full factorial design or half factorial design or central composite design, that is CCD, so you are getting some combination of the input parameters. Carry out experiment. Find out the responses. If the 3 variables are cutting speed, feed and depth of cut, I know their minimum and maximum. Okay. And what is the output? That is the quality of surface. That is the surface roughness or the surface finish. Surface finish is actually the mathematical concept. Surface finish cannot be measured physically. Surface finish is measured indirectly with the help of surface roughness. All of you know that. Okay. Now, supposing that surface roughness is the response. Okay. So, you carry out with all the input combination that particular experiment and find out for each of the combination of the input parameters what is the response, what is the surface roughness. Now, once you've got that particular, the picture of the complete table input-output relationship, now I can fit some regression equation. It could be a linear equation or it could be a nonlinear equation with square term, interaction term and all such things. Okay. So, the surface roughness will be represented as a function of the input parameter, that is cutting speed, feed and depth of cut, following the principle of the least square error. Okay, and remember once again you go back to the how to put a tent as accurately as possible so that there should not be any such wrinkle sort of thing and it is a very smooth tent. Once again there we are following the least square technique. Okay, we try to minimize the error in while making that particular tent ready. Okay, by putting proper pillars and putting proper tents and all such things. Okay, same thing we do it here mathematically. We try to find out what is the error in fitting for this particular your the set of data, and we use some optimization tool that is called the least square error fitting tool, and ultimately we could find out the statistical regression analysis and we can get the regression equation. It could be, as I told, that linear equation or it could be non-linear equation. Are you getting my point? That means we are able to find out the output as a function of the input parameters. So I'm writing here in the form of matrix. So O matrix is nothing but the output matrix. That is nothing but I have written here T matrix, you can see, multiplied by the I matrix. What is I matrix? I matrix is nothing but the input parameter. And what is our M? Our aim is to find out the output or the responses. So in the matrix form, output is nothing but matrix T multiplied by matrix I. Okay. So O is the output, I is the input, and T is the transformation matrix. Are you getting my point? Now this particular transformation matrix is very important. Now if I can carry out the regression analysis, I'll be getting this particular your transformation matrix, T matrix. Okay. And this is what I mean by the forward mapping. How to carry out reverse mapping? Now the both the sides you multiplied by T inverse. That is the inverse of the transformation matrix. So if you multiply both the sides by T inverse, so you'll be getting here T inverse multiplied by O matrix is nothing but I. Now here output is known, and I have to select that particular set of inputs so that I can reach the desired set of output. Okay, so T inverse multiplied by the output matrix is nothing but I. That is called the reverse mapping. Okay, but remember one thing, if you want to carry out so this particular reverse mapping, then the transformation matrix has to be invertible. That means you should be able to find out the inverse of this particular the transformation matrix. Okay, in other words, the transformation matrix has to be non-singular. Okay, so how to find out the inverse of a matrix, all of you know. Okay, I'm not going to discuss that particular thing. Okay, but remember the transformation matrix has to be invertible if you want to carry out so this particular the reverse mapping. Now here lies the problem. Okay, the problem lies with this particular fact, because in conventional statistical regression analysis, it will be very easy to carry out the forward mapping, but it may not be always possible to carry out the reverse mapping because transformation matrix may not be always invertible. It may not be always non-singular. Okay, and that is why we'll have to depend on your the non-conventional or unconventional fuzzy logic based or neural network based approaches. Okay, now with this particular knowledge, we are going to concentrate on how to carry out the regression analysis or how to carry out the forward mapping and reverse mapping using the fuzzy logic based approach. Now, before I start with discussing the fuzzy logic based approach, let me give you in very brief some introduction to fuzzy logic. Okay, then I'll proceed with this because all of you may not have that particular introductory knowledge on fuzzy logic. Okay, now remember, all of you are conversant with the classical set or the crisp set based on which the probability theory is working. All of you have studied probability theory. You know that the probability varies from 0 to 1, and this is a very efficient tool for handling your imprecision and uncertainty sort of thing. Okay, and probability theory works based on the principle of your classical set or the crisp set, which all of you have studied, might be in your higher secondary level or might be in the first year of your graduation. All of you have studied that. Okay, now today I'll be talking about another set that is called the fuzzy set. Now, what is the difference between a classical set or a crisp set and a fuzzy set? A crisp set or a classical set has got a well-defined boundary. On the other hand, the fuzzy set does not have a very well-defined boundary, or it has some sort of vague or imprecise boundary. Okay, now let me take a very simple example. You'll understand. Okay, as I told, I'll not be going for the mathematics. Mathematics are all available in my book. I'm just going to take a number of practical example, physical example, so that I can give you some idea in less time. Okay, let me take one very simple example. Okay, and very practical example also. Now, supposing that one of your friend is going to market and you are going to request, please bring 1 kg red apple for me. Now, this particular example is so good that I've kept in my textbook also. Okay, and this particular example is going to tell you the difference between the classical set and the fuzzy set. Now, Supposing that your friend is going to the market and you have told, you have requested that please bring 1 kg red apple for me. Now your friend will bring some apple and give it to you. And after receiving the apple, now if somebody asks, what is the probability that you got the apple? Depending on the situation, there will be a numerical value lying between 0 and 1 of the probability of getting apple. Are you getting my point? So you'll be getting apple with some probability value. And this probability is nothing but it depends on your the classical set or the crisp set which all of you have studied. Now I'm just going to ask you another, the more difficult question. After receiving this particular apple, if I ask you, what is the guarantee, not probability? So what is the guarantee that you got the apple according to your choice? That means you wanted some red apple. Now what is the guarantee that you got that particular, the red apple? Can you answer? Using the principle of classical set, answer is no. Nobody will be able to give guarantee that this is a red color apple, red apple. Okay, and this particular definition of the red will vary from person to person. Okay, so for the same apple, somebody will say it is perfectly red. Some other people will say it is slightly red. Some other people say, no, this is almost red, and so on. The same apple will be called in different way. That means there is fuzziness in the definition of the color red. And if you want to capture that particular fuzziness, your classical set is not going to help you, but you have to take the help of fuzzy set. So in fuzzy set, the color red will be defined something like this. It is red with membership function value or degree of belongingness, not probability, which will lie between 0 and 1. Okay. Now it is red with membership function value 0.4. The same apple, somebody else will say it is red with membership function value 0.5. Another person will say it is red with membership function value 0.6. Are you getting my point? Or they may say it is red with 0.5, it is red with 0.6, it is red with 0.7. So it is more difficult to measure the fuzziness of that particular color red. And we'll have to take the help of fuzzy set. The crisp set is going to give you one answer. What is the probability of getting apple? But what is the guarantee that the apple is red? That particular question will not be answered using the classical set. And to get an answer to that particular query, you'll have to go for the concept of fuzzy set. Okay, so I hope you got at least some idea between the classical set, the difference between the classical set and the fuzzy set. Let me take another very simple example. Things will be much more clear. Okay, supposing that today you are going to invite your friends for a dinner party. Might be at 8 p.m. So you have told one location that you come to this restaurant, okay, for today's dinner party. Come at 8. Supposing that you have got, say, 200 friends. You have invited 200 friends. Out of 200 friends, some of your friends will be coming, might be at 10 minutes past 8, that is 8:10 p.m. Some of your friends will become even before 8, might be 7:55 p.m. And some of your friends, but very less in number, will come exactly at 8 p.m. Okay. Now, for this 8 p.m., We have got a crisp set, we have got a fuzzy set. What is the crisp set? The crisp set is exactly at 8 p.m. If your friend comes exactly at 8, then he has come at 8. Otherwise, no. Are you getting my point? According to the classical set or the crisp set. But according to fuzzy set, the friends who are coming at 7:55 p.m. and who are coming at 10 minutes past, say, 8, all are coming for the dinner party at 8 with some membership function value or the degree of belongingness. This is what is mean by the fuzzy set. So I hope you got the difference between the classical set and this particular the fuzzy set. And I hope you have also understood which one is the more practical way of looking into the problem. Okay, so classical set 8 p.m. very difficult to achieve. On the other hand, the your 8 p.m. according to fuzzy set is more easy or easier to achieve. Okay, so I hope you got the difference between the classical set and the fuzzy set. Now this fuzzy set has got a number of applications. Out of all such applications, the most popular one is in the form of fuzzy reasoning tool. In short, this is also known as FLC, that is fuzzy logic controller. Okay. Now this fuzzy reasoning tool, we use the principle of fuzzy sets just to identify or establish the input-output relationship of a process. Now, if you see the literature, we have got two very popular approaches. One is called the Mamdani approach, another is called the Takagi and Sugeno's approach. The purpose is to establish the input-output relationship of the process. Now remember, each of these particular approaches, like whether it is Mamdani approach or Takagi or Sugeno's approach, it is having its own merits and demerits. Those things I'll simply point it out after some time. But let us see how to model the input-output relationship using the Mamdani approach, and then we'll concentrate on Takagi and Sugeno's approach. Now, supposing that I have got a process, and this process is having a few inputs and a few outputs. Okay, so might be say 4 or 5 inputs and say the 2 outputs we have. Now here you can see I have written process to be controlled. So you'll have to write down the name of that particular process. There are some condition variables. The condition variables are nothing but the input variables, and there could be some action variable that is nothing but is the output variable. Once again, let me try to take one very practical example. Now, let me take the same example of the room in which you are sitting to attend this particular class. Now, supposing that in that particular room, there is one air conditioner. Now, depending on the requirement, you'll have to adjust the angle of valve opening of that particular air conditioner. Okay. Now, if you want to sit comfortably inside the room, a few things you'll have to control. What is that? That is nothing but the temperature and humidity of this particular room. Those are nothing but our action variables. Okay, that is actually our requirement. But what are the input condition? The temperature and humidity of this particular room depends on a number of parameters. What are those? For example, it depends on the temperature of outside, that is the atmospheric temperature. It depends on the pressure, that is the atmospheric pressure. It depends on the people sitting in this particular room, okay, it depends on the temperature and humidity inside this particular room. It depends on the thermal conductivity of the wall of your room and so on. But you'll have to maintain the temperature and humidity of this particular room in a comfortable zone so that you can sit comfortably. Okay, and with the help of a air conditioner, you'll have to control the angle of valve opening accordingly so that you can keep the temperature and humidity of this room in a very comfortable way. Now here in Mamdani approach, what we do is these condition variables, the input variables, those things will pass through one fuzzification module. What is that fuzzification module? To discuss the fuzzification module, actually I'll have to concentrate on the membership function distribution of the input parameters or the input variables. What are those? Now I'm just requesting you, you open your notebook and I'm just going to give you some instruction and accordingly you prepare one drawing. Okay. So all of you, please open your notebook. I think notebook is ready now. Okay. You draw X and Y axis. X axis you draw, Y axis you draw. And there will be an origin having the coordinates say 0, 0. Have you drawn it? I hope so. Now along the X axis, you write down a few numbers after maintaining the scale. Okay. So the origin is 0, 0. The first point along x-axis you write down, it is 5, 0. Second point you write down 10, 0. Third point you write down 15, 0 and so on. Okay. I hope you have drawn these 3 points with coordinates along the x-axis. Now you concentrate on the y-axis. Okay, along the y-axis, origin is your 0, 0. You take another point, following another scale that is nothing but whose coordinate is 0, 1. Okay, so along the y-axis, you draw one point 0, 1. I hope all of you are able to draw this. Okay. Now what you do is along the x-axis, you write down temperature. You write down temperature with some unit, say degree centigrade or whatever maybe, or you forget about the unit. I want to simply take one example. That's all. Now along the y-axis, one point is 0, 0, another is 0, 1. There you write down membership function value or membership value. Membership value. And the range of membership value is 0 to 1. Okay, just like the probability. But probability and membership value are not the same. Let me repeat the definition of probability and membership value. Probability is nothing but a frequency data. Okay, are you getting my point? And the probability of getting apple will depend on the frequency data, depending on the season, availability of the apple in the market. Okay, so that is a frequency data. But membership is nothing but degree of belongingness. Are you getting my point? How much red that particular apple is, that type of the membership value or degree of belongingness, that will also vary from 0 to 1. Okay, so like probability but the concept of probability and concept of membership are totally different. Membership concept depends on fuzzy set, probability depends on classical set. Okay, so here I am concentrating on the membership value. Now, once you have drawn these 4 points and including the origin 5 points, you concentrate on the point 0, 1. Go to the point 0, 1. Okay. Now through this 0, 1, you draw one horizontal line which is parallel to the x-axis. Draw one line parallel to x-axis. Okay. I think all of you are able to draw. Okay. Now you concentrate on the point 5, 0. Okay. 5, 0. Draw one vertical line, and this vertical line is going to intersect that particular horizontal line which was drawn parallel to x. Okay, you draw that particular point. You go to the next point 10, 0. Concentrate on the point 10, 0. Okay, draw another vertical line which is also going to intersect that particular horizontal line. Draw another vertical line at the point 15, 0, and it is going to concentrate on that parallel line. I think all of you have got it. Okay. Now, you do one thing. Now, what is the coordinate lying on the parallel line? It is very simple. The coordinate of the intersection point, it will be 5, 1. Okay. The next it will be 10, 1, and next intersection point will be your 15, 1. I think I'm clear to all of you. Okay. Now, you join the point 0, 0 and 5, 1 by a straight line. So I have got a straight line. Then you join the point 5, 1 and 10.0. You'll be getting another straight line. Now I'm able to draw one triangle. Can you see that? Next, you concentrate on 5, 0 and the point 10, 1 joined by a straight line. So I have joined. Then you join the point 10, 1 and 15, 0. So I'll be getting another straight line. So I'll be able to draw another triangle. I hope you have seen. Okay. Now you join the point 10, 0 and 15.1 by a straight line. And you join the point 5, 0 and 0, 1 by another straight line. What are you getting? You are getting two isosceles triangle and two right angle triangle. I think I am clear to all of you. Okay. Now, the input parameters, for example, temperature, humidity, thermal conductivity of the wall. So I'll have to express this type of membership function distribution. This is called the triangular membership function distribution for temperature. Okay. Now, the first right angle triangle, if I write down, this is very low temperature. Then the first isosceles counting from the left side will be low temperature isosceles triangle. Then the second isosceles triangle will be your high temperature, and the last right angle triangle will be very high temperature. Can you see that? So you'll be getting some membership function distribution. Similarly, for all the inputs and all the output parameters, you'll be getting the membership function distribution. Initially, you'll have to design based on your experience of the problem, and after that, you can take the help of some optimization algorithm, and with the help of some known input-output data, So it will be able to find out the optimal distribution of the membership. Okay, that I will be discussing after some time. Okay, now supposing that I have got 5 input variables. Out of these 5 input variables, one is temperature, and I have got this particular membership function distribution. The moment I pass the temperature, so might be temperature is 12 degrees centigrade or whatever may be. Okay, now corresponding to this 12, I'll be getting, if I just draw one vertical line parallel to y, what will happen? It is going to intersect to the triangle, that is a very high triangle and the high triangle. Can you see that? So it is going to intersect both high as well as very high temperature triangle. So I'll be getting some membership function value lying between 0 and 1 corresponding to very high, and another membership function value I'll be getting corresponding to your high. Okay, so I'll be getting two membership values or degree of belongingness. This is what we mean by fuzzification. So corresponding to the input parameters, if you can find out the membership function value or the degree of belongingness, that is what we mean by your fuzzification module. So for each of the input parameters, we should be able to find out the membership function values or degree of belongingness. Okay. Now, supposing that, let me take a very simple example. Supposing that I have got 2 inputs and 1 output system, say, for simplicity. Input I1 has got say 4 linguistic terms, like very low, high, and very high. And the second input has got another 4 linguistic terms, say humidity. Okay, once again, very low, high, and very high. So 4 multiplied by 4, there will be 16 possible combinations of the inputs. And for each of the possible combinations, there will be some output. Okay. Now those input-output relationship will be expressed with the help of some rules. What could be the rules? The rule could be as follows. If temperature is low and humidity is high, then the output angle of valve opening for the air conditioner is medium. That type of thing. This is one rule. Similarly, we have got say 16 such rules. Now, the rules are made ready, all 16 rules are made ready, and depending on the set of inputs, and whenever we are passing one set of inputs, so out of those 16 rules at a time, there could be a maximum of 4 fired rules. And for each of the fired rules, I'll be getting some output. Now, out of those 16 rules, which are going to be fired, that is decided by the fuzzy inference engine. So fuzzy inference engine is going to find out of these 16 rules, which are going to be fired corresponding to that particular set of rules. Okay, that is the function of fuzzy inference engine. And once it has got fired, I'll be getting the output for each of the fired rule. But that output will be what? Output will be nothing but the area of the membership function distribution of the output, that is nothing but angle of valve opening. So once again, temperature, humidity, and angle of valve opening, that is the output, you'll have to consider some membership function distribution. I'm just going to take one example and see. Okay. That means using the fuzzy inference engine, we are able to find out some output, and that particular output is nothing but the fuzzified output, because that is nothing but the area. Now, if it is a fuzzified output, it is not crisp, but the angle of valve opening has to be crisp. For example, the valve, whether it has to be opened towards the clockwise or towards the anti-clockwise by some angle, that type of decision has to be taken. And that particular decision is a crisp decision. Okay. So from this fuzzified output, you'll have to find out the crisp output. How to find out? You'll have to take the help of your defuzzification module. Okay. So once you have used the defuzzification module, now you are in a position to take that crisp action. Okay. That is actually, in short, the working principle of Mamdani approach of fuzzy reasoning tool. Okay. Now, how to determine the output corresponding to a fired rule? That I'm going to discuss with the help of, say, this particular the figure. Supposing that, say, out of 16 rules, say, hypothetical, only 2 rules are going to be fired. What are the rules? The fired rule 1, if S1 is A1, that is the first input, and this is the membership function distribution for the first input, that is temperature. And S2 is B1, that could be the membership function distribution for the humidity. Okay. Then the output is nothing but the C1. So this is the membership function distribution for C1. Supposing that this is a fired rule. How to determine the output of this fired rule? It is very simple. Here you can see I've used one AND operator in Mamdani approach. If S1 is A1 and S2 is B1, then A prime is C1. Now this particular AND is capital A and D. Have you seen that? So this is not the conjunction AND. This is the operator AND. And what do you mean by the operator AND? This operator AND is nothing but the mean operator. So this mean operator is going to determine the minimum. The moment I am passing S1 star and S2 star, corresponding to S1 star, I will be getting some mu value here. Corresponding to S2 star, I will be getting another mu value here. And these two mu values will have to compare, and you'll have to find out the minimum value of mu. And corresponding to the minimum value of this particular the mu, I will be getting that particular the output. So I will be getting with the help of this particular thing. So you can find out the truncated triangle, and that is nothing but is your the output. Okay. So this is the output, and corresponding to this fired rule, so I will be getting your, this is the output. Similarly, you concentrate on the fired rule 2. The fired rule 2 is if S1 is A2 and S2 is B2, then A prime is C2. Okay. So this is the fired rule. So corresponding to S1 star, you get some mu value. Corresponding to S2 star, you get some mu value. You compare, find out the minimum. So I will be getting the output corresponding to this particular the fired rule. Okay. Now you see, just a minute. Now you see, corresponding to your, so this particular, I will be getting the 2 output. I will be getting the 2 output corresponding to each of the fired rule. And now I have to combine the output. How to combine? To combine the output, we are going to use one AND operator, and using that particular AND operator, which is nothing but the union operator, we can find out the maximum. So corresponding to this particular Fayed rule, I'll be getting one truncated triangle here. Corresponding to this particular Fayed rule, I'll be getting another truncated triangle here, and I'll have to superimpose, and this is nothing but the output of the combined Fayed rule. Okay, and then we'll have to find out the crisp output using the defugification module. Okay, now if you see the literature, we have got different types of defugification methods. For example, we have got the center of sums method. It is very simple. For each of the truncated triangle, you find out the area and center of area. For example, say for the first Fayed rule, I can find out the area and center of area. Second Fayed rule, I can find out the area and center of area. Okay, then we combine and we try to find out the crisp output. So this is actually the most widely used method of defugification, but it has got its own merits and demerits. What is the demerit? Demerit is one common zone will be considered more than once, which is not desirable. Okay, for example, so this particular zone, for example, if you see this particular zone will be considered, twice. So there will be little bit of error. Now to avoid that, so we'll go for another method that is called the centroid method. What is the centroid method? We know the fugified output, and this particular area that is divided into a large number of regular subregions. For example, here I will have one right angle triangle. I've got one rectangle. I've got one triangle here, another rectangle, another triangle sort of thing. And for each of these regular subregion, like right angle triangle, rectangle, I can find out the area and center of area. And once you've got it, the area and center of area, so I can use this method of defugification. Are you getting my point? So this is centroid method, and both the center of sums method and centroid method are computationally expansive. And that is why we go for another method that is called mean of maxima method. What is that? So this particular area is nothing but the output of the combined controls action considering the rules. Now what we do is we try to find out the range for the output for which we get the maximum value of membership. That particular range we consider, find out the midpoint of that particular range, that will be the crisp output. Okay, and this is called the mean of maxima method. Okay, mean of maxima method. Okay, so this mean of maxima method, although it is very approximate, but computationally it is very fast. Okay, so this is the way actually you can find out the crisp output corresponding to your fugified output. Okay, so I hope you got some idea of the Mamdani approach of fuzzy reasoning tool. And using this Mamdani approach of fuzzy reasoning tool, very easily you can model the input-output relationship of the process. Okay. Now this approach is having its own merits and demerits. For example, its interpretability is very good, but accuracy may not be so much good for this Mamdani approach, because if you want more accurate modeling of the input-output relationship, we want more number of linguistic terms, and more number of linguistic terms means more number of rules, and computationally it will become very expensive. Okay, and this Takagi-Sugane's approach is another very popular approach of developing the fuzzy reasoning tool. Here we will be getting better accuracy, but at the cost of your interpretability. Okay, that means if you read a particular rule, its output will not be able to visualize. Okay, now let us see the principle of this Takagi and Sugena's approach. Now, in Takagi and Sugena's approach, a rule is composed of fuzzy antecedent and functional consequent part. Antecedent is nothing but the input parameters, and consequent is nothing but the output parameters. Okay, and according to this approach, a rule will look as follows. The ith rule is represented as follows. If x1 is a1i and x2 is a2i, and the last is if xn is ani, then yi is nothing but a0i plus a1i x1, and the last term is ani xn. Okay, and here you can see we use the conjunction end, not the operator end. Okay, so this is conjunction end, conjunction end. Okay, so in Mamdani approach we use capital A and D, but here we use small a and d. Okay, and here the output of the ith rule is expressed as the function of the input parameter. Here we consider the linear function. So yi is nothing but a0i plus a1i x1. The last term is ani xn. So this is a particular rule according to Takagi and Sugeno's approach. And here a0, a1, an are nothing but the coefficients. Now in Takagi and Sugeno's approach, a nonlinear system is considered to a combination of several linear systems. So approximately one nonlinear system can be modeled as a combination of several linear systems. But here the weight of a particular rule, the ith rule, is determined in a slightly different way. How to determine? The weight of the ith rule, that is wi, is nothing but mu a1i corresponding to x1 multiplied by mu a2i corresponding to x2 multiplied by mu ani corresponding to xn. So here all the mu values I'm just going to multiply. If you remember in Mamdani approach, how to determine the weight of the fired rule? We consider the AND operator. The minimum of 2 or 3, the mu value, that is a membership function value, we consider as the weight of the fired rule. But here, the weight of the fired rule is determined using the multiplication operator, something like this. And once you've got the weight of the ith rule, and if I know the output of the ith rule, then the combined control action is determined as y is nothing but summation I equals to 1 to k wiyi divided by summation I equals to 1 to k wi. K indicates the total number of rules. Are you getting my point? So very easily you can find out what should be the combined control action. And this particular combined control action is nothing but the output. So using this particular the Takagi and Sugena's approach, you can find out the input-output relationship. Now another thing we did, and I just want to spend some time on that, that is called cluster-wise regression analysis. Okay. Long back we did, I think 2005 or something. Now this cluster-wise regression analysis what was the philosophy? The philosophy was how to obtain more accurate input-output relationship of a particular the process. So what we did, depending on the similarity and using the principle of the fuzzy clustering, okay, we just made a few clusters depending on the similarity. There are some algorithms like fuzzy Siemens clustering algorithms, entropy-based clustering algorithms, and so on. Okay, so using those clustering algorithms, you can find out the clusters, and in a clusters, the data points which are lying inside the cluster, they should have good similarity, but the two data points belonging to two separate clusters could be different or must be different. Okay, so depending on the similarity, we can form the clusters. Okay, now within the clusters, we do some sort of regression analysis, input output relationship. Supposing that in a particular data set for which we want to make the input output relationship, at first we can go for clustering based on similarity. Okay, say there are 4 clusters depending on the similarity. The moment a new data is coming, one set of new inputs are coming and its corresponding output is to be determined. So what we do is we try to find out the similarity of that particular new test data with the 4 clusters. Okay, and once you've got that particular similarity, now we are in a position to find out what could be the input output relationship in a more accurate way. Okay, so that is called the cluster wise regression analysis. So using that cluster wise regression analysis, there is a possibility you can find out the input output relationship more accurately. Okay, so I hope I'm clear like how to use the concept of fuzzy logic to make the input output modeling. You can do both forward mapping as well as the reverse mapping using the fuzzy reasoning tool. Okay, now another tool which is going to help you in input output modeling is the neural networks. Okay, now supposing that we have got a large number of variables like say weather forecasting. Like you'll have to make some input output relationship based on the weather forecasting. Now remember, weather forecasting is a very difficult problem to tackle, and this problem involves a large number of input parameters, input variables. Okay, now if I want to tackle using the concept of fuzzy logic, so I'll have to design a very large number of rules. And if I design a large number of tools, what will happen to the complexity? The complexity is going to increase. Okay, so for tackling the problem involving a large number of variables, it may not be always advisable to go for the fuzzy reasoning tool. And there we'll have to depend on the neural networks. Okay, now once again, whether it is fuzzy logic or neural networks, our aim is to model the human brain in the artificial way. Okay, the performance of fuzzy reasoning tool, you must have seen while discussing, I mentioned that it depends on the membership function distribution of the input and output variables. That is what is known as the database of the fuzzy reasoning tool. That is called the database, DB. Okay, and it has got the rule base. Okay, that is RB. And considering both database and rule base, that is known as the knowledge base. Now, the performance of a human being or the performance of a human brain depends on its knowledge base. For example, I'm trying to teach you something and you are going to learn something. While learning, you are developing or training your own brain, your own knowledge base. Are you getting my point? So the purpose of using these neural networks, okay, is to model the human brain in the artificial way so that we can establish the input-output relationship. Now, if you see the literature, a huge literature is available on different types of neural networks. Okay, some of the networks used for input-output modeling, I'll be discussing. I'll try my level best to give you the information of those neural networks. But before I start with neural networks, let me tell you once again that our brain consists of a large or number of neurons. Right? The working principle of a neuron, the structure of a neuron, those things you have studied in your school level biology or life science course. Okay. The same neuron, the working principle of a neuron, we are going to copy here in the artificial way. That is called the artificial neuron. And in a layer, there could be a large number of neurons. And similarly, in one neural network, consists of say either 2 layers or 3 layers or even more than 3 layers. Okay, so you'll be getting that particular the neural network. Now, what is the purpose of using this particular neural network or fuzzy reasoning tool to express the input-output relationship of a process? Idea is very simple. Idea is how to represent or how to capture the input-output relationship of a particular the process. Are you getting my point? And if you see our brain is very complex. Here we have got about 10 raised to the power 11 or 10 raised to the power 12 neurons. Of course, it will vary from person to person. And those neurons are operating in parallel. Are you getting my point? And that is why our brain is nothing but a highly complex parallel computer. Okay, our brain, let me repeat, is nothing but a highly complex parallel computer. Okay, and it is very difficult to model our brain in the artificial way. Although throughout the world, many people are working in the field of artificial intelligence or computational intelligence, that is nothing but artificial intelligence using the principle of soft computing. It is extremely difficult to model and develop a human brain in the artificial way. Okay, but some trials are made so that at least some part can be modeled and we can use in industry problem just to find out some acceptable solution related to input-output relationship of the process so that you can automate that particular the process. Now, as I told that I'll not be able to discuss all the networks in detail, but some of the networks I'll be discussing which are very much essential to establish the input-output relationship. Now, the first network which I'm going to discuss is nothing but a multi-layered feed-forward neural network. In short, that is known as multi-layer MLFFNN. Now remember, this is popularly known as the backpropagation neural network in most of the literature. But that particular name is not correct. The correct name is your multi-layered feed-forward network, neural network. Okay, that can be trained using either backpropagation algorithm, that is BP algorithm, or you can use some other optimizer, some nature-inspired optimization tool like genetic algorithm or particle swarm optimization or some other tool. Okay. Now, if it is trained by backpropagation algorithm, that is called backpropagation neural network BPNN. If is trained using genetic algorithm, that is called genetic neural system or GNN. I'll be discussing after, might be in the next class. Okay. And if you use PSO to train this particular network, that will be known as PSONN and so on. Okay. But let us see how does it work. Okay. What is the working principle of this multi-layered feed-forward network? It is very simple. Okay. So once again, our aim is to establish the input-output relationship. Here I am considering that there are capital M inputs and we have got capital P number of outputs. Our aim is to establish the input-output relationship. We take the help of three layers, say input layer, hidden layer, and output layer. There are capital M inputs on the input layer. There are capital N neurons on the hidden layer and capital P neurons on the output layer. Each particular neuron will be indicated by a circle. Okay. Inside the circle, in fact, we have got the summing junction and we have got the transfer function. Now, the function of a transfer function is to convert the input to the output. Okay. I will see. Now, on the input layer, we have considered, say, the linear transfer function y equals to x. In the hidden layer, say, we are considering some nonlinear transfer function like log sigmoid transfer function. On the output layer, we are considering another, your nonlinear transfer function, the tan sigmoid transfer function. And all of you know, if I use log sigmoid transfer function, output will lie between 0 and 1. Okay. And if I use tan sigmoid transfer function, the output will lie between -1 and +1. So I'm considering three layers, input layer, hidden layer, and output layer. The input layer and hidden layer, those are connected with the help of one connecting weight matrix that is denoted by V. Then the hidden layer and the output layer, these two layers are connected with the help of connecting weights denoted by W. So V and W are nothing but the connecting weights between the input and hidden and between the hidden and the output layers. Okay. And these particular connecting weights will lie between 0 and 1. And you can also consider from -1 to +1. And initially, those your connecting weights will be generated at random using the random number generator. Now, on the input layer, we pass the inputs, and remember, whenever we are going to use the neural network, so these new inputs are to be passed to the network in the normalized scale, either in a scale of 0 to 1 or from -1 to +1. And all of you know, I think, how to convert this particular input to the normalized scale. So I'm just going to help you how to convert these particular inputs to the normalized scale. Now, all of you, please use your notebook and pen. Please write down whatever I'm telling. X minus X minimum divided by X maximum minus X minimum. Have you written? Let me repeat. X minus X minimum divided by X max minus X minimum. Okay. Now you put on the numerator, you replace X by X minimum. How much you'll be getting? If you replace X by X minimum, you'll be getting 0. I think all of you are getting 0. 0 divided by something is 0. Okay. If you substitute x by x maximum, how much you'll be getting? You'll be getting 1. Okay. Although the x is in real scale, might be 10 to 500, you can convert it to 0 to 1 in the normalized scale. Are you getting my point? Another thing you try to do, another expression you write down, 2 into x minus x minimum, all of you write down, divided by x maximum minus x minimum minus 1. Let me repeat. 2 into x minus x minimum divided by x max minus x minimum. So numerator by denominator. After that you write down minus 1. Okay. Now you put x equals to x minimum. How much you'll be getting? X equals to x minimum. If you put, you'll be getting 0 minus 1. So you'll be getting minus 1. Next you put x equals to x maximum. How much you'll be getting? X equals to x maximum. If you put, it will be 2 minus 1. You'll be getting plus 1. So it will vary from minus 1 to plus 1. This is the way actually you can find out the normalized value corresponding to the inputs. Okay. Now on the input layer, we are using linear transfer function. The output is nothing but input. So the output of ith neuron lying on the input layer is nothing but the input of the ith neuron lying on the input layer. So all the outputs of the input layer you can find out. We know the connecting weight. So this output is multiplied by the connecting weight. And those are summed up here as the input of the hidden layer. Okay. So you'll be getting the input of the hidden layer is something like this. So you can find out Hi1, then comes your Hij, that is the input of the jth neuron lying on the hidden layer, then Hin, and here we use log sigmoid transfer function. Okay. So using this log sigmoid transfer function, that is 1 divided by 1 minus e raised to the power a1x or something like that. Okay. So this log sigmoid transfer function if you use, so I'll be getting that particular the output. Similarly, I'll be getting the output here. Hoj is nothing but output of the jth neuron lying on the hidden layer. And once you've got this particular output, you multiply it by the corresponding connecting weights. You sum them up and you'll be getting the input. And if you get this particular input, now you pass through the 10 sigmoid transfer function, you will be getting the output. And remember, this particular output will be in the normalized scale. Okay. So once again, you'll have to denormalize. The rule for normalization I have told you. So using that, you can also find out the rule for denormalization. Like from normalized value, you can also go to the real value. That is also possible. Okay. And once you've got this particular calculated output for a set of input, now we compare this particular calculated output with the target output, find out the deviation or the error, and that particular error will be fed back just to update or modify the connecting weights and the coefficient of transfer function so that it can model the input output relationship more accurately. Okay. So whatever error we are getting, that error is propagated back. If you are using the back propagation algorithm, we can modify the connecting weights, we can modify the coefficient of transfer function, and once it is trained with the help of some input-output relationship, known input-output relationship, following the batch mode of training, there is a possibility that this network will be able to make the prediction for some unknown test scenarios, okay, very accurately. Now, the mathematical expression for all such things, I've already written in my textbook. You can have a look, or you can follow my NPTEL lectures. I think tomorrow's class, I'll be giving you the link for the NPTEL lectures also. So the detailed mathematical calculation for all backpropagation algorithm and other algorithm, you'll be getting from my textbook and NPTEL lectures. Okay. Now, using this neural network, this multi-layered feed-forward network, you are able to capture the input-output relationship of any such engineering process or manufacturing process. Now, as I told, now we are going to start with your doubt clearing session. So based on whatever I could discuss, if you have any doubt, you are free to ask me, and I'll try my level best to clear your doubts. So let us go for the doubt clearing session first, and then tomorrow once again from 11 we are going to start from here, and I'll show you there are a few other tools. Okay, but let me stop my presentation for today. Now I'll listen to your problem, your doubts, and I'll try my level best to clear your doubts. So I'm just removing the PPT for the time being. Is it okay? Or shall I keep the PPT with you? Rasa Mahapatra? Shall I? Hello?
Yeah, participant. Hello, sir.
Shall I keep this particular PPT or shall I remove the PPT for the time being? Which will be easier for you?
If some participant are asking for any particular PPT, sir, then it will, if you are
Is there any doubt
PPT,
of the
yeah, participants, you can unmute yourself. If you have any specific doubt, you can ask.
Good afternoon, sir. This is Rajiv Gupta.
Good
sir,
afternoon.
I have one doubt here. Sir, we are doing normalizing our input parameters, but sir, we are having so many methods of normalizing, like linear normalizing, vector normalizing, enhanced accuracy method, logarithmic method. So, which method is best? Generally, we are using
the method which I told you. I hope you have written in a notebook. No, did you write that?
Yes, sir. This is a linear normalization.
So this method you follow. Unnecessarily don't make it complex. Okay. This is more than sufficient. You follow this method. Okay.
Okay. And sir, I have one more doubt. Sir, we are having
any other doubt?
Very big. Yes, sir. I have one more doubt. Sir, if we are having very big data set, from the big data set, we have to sample some data for our input. So, is this any method to sampling?
Actually, what we do is, supposing that we have got a large number of data set. Okay. Now, if you have got a large number of data set, some of the data set you'll have to use for training, and the other data set will be used for the testing purpose. Okay. Now, what you can do, we can use, there is a concept of that is called, just a minute, that is called K-fold design sort of thing, okay, or two-fold design. So the whole data set you can, if it is two-fold design, okay, so you make a classification of training data and test data. First use, say if you have 1000 data, 6000 or 500 data you can use for training, and the remaining 500 for testing. Okay, and then you simply just flip it. That means the test data used as a training data and the previous test data use as the test data and see the performance. That is called the two-fold or k-fold design. Okay. So that method also you can do. Or if it is five-fold, the whole data you can divide into 5 parts. Okay. So out of 5 parts might be 4. That means 80% you can use for training and the remaining 20% you can use for testing. But the training data and testing data, you just go on replacing. Okay. Are you getting my point?
Okay, sir. Okay. Yes, sir, got the
80%
point.
you are, so that way you can do. Okay.
Okay, sir. Thank you, sir.
Any other doubt?
Okay, any other question? Please unmute and you can ask.
Was it okay? The speed, is it okay? Is it understandable?
Yes, sir. Participant, you can respond.
Is it understandable? Shall I move with even slow speed or the speed is okay?
So I think speed is okay.
Okay, fine. So, Professor Mahapatra, then let us stop here today.
Yeah, actually Mahapatra sir is not here because of some urgent work he has to go. So yeah, so if any question, if no question from the participant, then you can stop
what's
here.
your name? Good name, please.
Sir, my name is Lieutenant Virendra Kumar Barik, one of the co-coordinator of this event.
Okay, Professor Barik. Okay.
Yes.
Okay, then shall I stop here today, or if there is any query, I can try. Okay,
let's once again I am asking to the participants if any specific participants, if you have any queries, please write down in the chat box, or you can unmute yourself and you can ask directly. Maybe they don't have doubts, sir.
Okay.
So, no, sir. One of the questions.
Tell me.
Yeah, in the chat box is written, sir, how to perform neurogenetic technique.
Neurogenetic, I'll be discussing tomorrow. Tomorrow morning, I'll be discussing. Okay. I'll be discussing tomorrow morning.
Tomorrow, tomorrow again we have the session from
11.
11 o'clock. Then we are going to.
So tomorrow I'm going to discuss like how to design the genetic neural system. Okay. Genetic neural, genetic fuzzy, neurophagy. I'll be discussing tomorrow, and how to use it for the input-output modeling. Okay.
Yeah, another question I think from Rajiv.
Please.
No, sir. I have not question, sir. I have one small question. Sir, I have completed your NPTEL course of fuzzy logic and neural network.
Very
now,
good.
Can you suggest me now what the next level course?
Next level course is actually now once again that fuzzy logic course and traditional and non-traditional optimization course will be running from this January, February. Okay. And robotics will be running from July. Robotics is now running. Okay. In NPTEL. Okay. And your next higher level course, I have not developed anything till now. But what you can do is you can concentrate more on the recent network like convolution network, CNN network, and that type of thing. Okay, and related to fuzzy sets, fuzzy logic, like you can concentrate more on grammar of fuzzy sets, fuzzy entropy, and that type of thing, uncertainty modeling in much more detail. Those things are not included in that NPTEL course. Okay.
Okay.
CNN also is not included in that NPTEL course. Okay, so those things you can study. Then there is another network which is not included, that is called bidirectional associative memory. That particular network also you can study. Okay, there are a few other networks which are not included, like probabilistic network and that type of thing. Those things you can study, like in future.
Okay, sir. Okay, sir. Thank you, sir.
Okay. Any other doubts?
Sir,
Okay, then let me stop here today. Tomorrow we are
yes,
going
sir, we
to
can.
meet at
Yeah.
11. Okay.
Yes, sir. Tomorrow again we are going to meet at
So
11.
I'm not just coming out from here meeting. Okay.
Okay, sir. Thank you very much, sir,
Thank
for
you
the
very
today's
much.
session. Yes, sir. Tomorrow again we will meet. Okay.
Okay. Okay. Fine. Fine.